Your lab experience so far with redox reactions is with using the activity series to identify single displacement reactions. We use the activity series to decide when a metal will react with water, when it will react with an acid, or when one metal will displace the electrons in another. So for example, if I have a container of copper nitrate or sulfate solution, and I put a zinc bar into that solution, what's going to happen is a redox reaction. The copper ions will gain electrons from the zinc atoms, and the zinc atoms will go into the solution while the copper atoms will adhere to the surface of the zinc. You did an experiment last year similar with aluminum in place, and you formed copper on the surface of the aluminum. Now this reaction is arising because of an electron transfer, and the electron transfer is actually happening right at the surface of the metal. So what we want to do is we want to make available those electrons that are being transferred and use the electrical energy that's available. In order to do that, we need to set up a galvanic cell. And what a galvanic cell is going to do is it's going to separate the oxidation reaction from the reduction reaction, and it's going to allow the electrons to travel through a wire. And while they're traveling through a wire, we'll be able to make use of the electricity that's generated. So we can measure the voltage, or we could connect a light bulb, or in examples of your laptop or any device that you use that has a battery in it, it's the same principles are being used. We're using a redox reaction and harnessing the electrical energy that's produced in order to make use of it. The Daniell cell is one of the original galvanic cells, and it was set up using this zinc and copper reaction. And like I said, when we want to set up a galvanic cell, what we need to do is we need to separate the oxidation reaction from the reduction reaction. And we do this by creating two cells. So this cell over here consists of an anode, which is a zinc bar in a zinc solution. And we've got a cathode of a copper bar in a copper solution. And we connect the two metals to one another using a wire. Now what happens is the zinc on this side is losing electrons and going into a solution. The electrons are traveling along the wire from the anode to the cathode, and the electrons are being collected at the cathode by the copper ions in solution to produce copper atoms. By separating the oxidation reaction from the reduction reaction and allowing the electrons to travel from one to the other, we are able to harness the electrical energy. So if we've got a light bulb here, we can turn that light bulb on if there's enough voltage produced by this reaction. Now I've used the words anode and cathode. The anode is the electrode where the oxidation takes place, while the cathode is the electrode where the reduction takes place. Okay, you can remember which one's which in a few different ways. Anode and oxidation both start with vowels, while reduction and cathode both start with consonants. You can also remember that where oxidation is occurring, the electrons are being produced, so this is negative, as is an anion, while on the other side, where the electrons are being collected, it's going to be positive, which is the cathode. A silly way to remember it, thinking back to Leo the lion says grr, okay, what I do is I think of it as Leo has the hiccups. Instead of saying grr, he says gurk, and gain of electrons is reduction at the cathode. Okay, so there's lots of ways that you can remember that, but you need to know that the oxidation is occurring at the anode and reduction is occurring at the cathode. Now, another part of the galvanic cell that's really important is this salt bridge here. Okay, the salt bridge is necessary in order to allow the reaction to continue, and I'll explain why. If we think about this half cell, in this reaction, what's happening are copper ions are gaining electrons to produce copper. As this reaction proceeds, we're actually removing copper ions from the solution. And so if we let it go for an extended period of time, what's going to happen is overall this solution is going to have a negative charge. It's going to lose its electric neutrality. And that is unfavorable for a solution. It does not want to be charged. So if it does end up being charged, the reaction will stop. What the salt bridge does is it provides an inert solution, so a solution that won't react with the other species in the container. And what happens is the ions are able to migrate from the salt bridge into the beaker in order to help maintain electric neutrality. So in this case, because we are taking the positive ions away, the positive ions from the salt bridge will migrate into this solution. When you do this experiment, you'll have experience with the salt bridge, and you'll see that it's a glass tube with a solution in it, and it's got a plug on it that allows for the ions to migrate from one to the other. The same discussion can happen for the anode. Okay? At the anode, the reaction that's happening is the zinc is losing electrons to produce zinc 2+ ions. So as the reaction proceeds, zinc 2+ ions are collecting in this beaker. And so over time, this container will actually become more positive. So from the salt bridge, the anions migrate to the anode in order to maintain electric neutrality. You'll see when we do the experiment, if you take the salt bridge out, this light bulb goes off. The reaction ceases. Now we can represent a cell using such a diagram with the beakers and with the anodes and the cathodes, etc. But there's also another notation that we can use that's much simpler, and this is called galvanic cell notation. This notation represents this cell. When you use galvanic cell notation, what you need to do is place the anode on the left-hand side always. So in this case, we've got zinc in a zinc solution. This vertical line represents the separation of the two in terms of their states. So you've got a solid in the solution. This solution is connected to a copper solution that is connected by a salt bridge, which is what this double line represents. And the copper cathode is placed in that copper solution. What's nice about this notation is you can actually see both the anode and cathode reactions that are happening. The zinc is being converted to zinc 2+, and the copper 2+ at the cathode is being converted to copper. Let's look at some examples. In this first example, we're going to sketch and label a galvanic cell that makes use of the following spontaneous reaction. And we're also going to show the cell notation for this cell. One important thing to note about this is that it specifies that it's a spontaneous reaction, and that is one of the features of a galvanic cell. Galvanic cells are spontaneous reactions. Okay, we're going to see cells later on that are non-spontaneous. So these are reactions that are favorable based on the activity series. So the substance that is more likely to gain electrons will, as is denoted from the activity series. So in this reaction here, we've got magnesium going to magnesium 2+, and we've got iron going to iron atoms. So in this case, the magnesium is being oxidized, so it's going to be at the anode, and the iron is being reduced or gaining electrons, and it's going to be at the cathode. To set up the cell, okay, you need a beaker with the appropriate metal. So we've got magnesium bar in a magnesium solution. Connected to an iron bar in an iron solution, it's 2+. Okay, and the anode is connected to the cathode. Okay, we can attach a voltmeter here or a light bulb if we want to. The electrons are traveling, and they always do, from the anode to the cathode. We can show the reaction. So the magnesium here is losing electrons, So that's the reaction that's occurring at the anode, and the reaction that's occurring at the cathode is the reduction of iron ions to Fe. Now we also need to show a salt bridge because this reaction would not occur without a salt bridge. One thing about the salt that you choose for the salt bridge is that you want it to be something that is inert, that will not react with the other substances in either of the beakers. In the example that we looked at before, we used KCl, which is very useful in a lot of cases, but it can be a bit of a problem. So if we were doing a reaction that involved silver, for example, that could precipitate. The chloride and the silver will form a precipitate, and so that's not a good choice for a salt bridge solution. So I like to use potassium nitrate because both potassium and nitrate have very low reactivity, and they are don't form precipitates with anything, so they end up being a good choice. Now to do the cell notation for this, we need to make sure that the anode is on the left. Okay? For this galvanic cell picture, we could have drawn it the other way. It wouldn't matter as long as we show the correct direction of the electrons. But with cell notation, it is a must that we have the anode on the left, and in this case, we've got a magnesium bar in a magnesium solution connected by a salt bridge to an iron solution which has an iron cathode in it. Now in the previous example we showed the concentrations being 1 mole per liter. That is the standard concentration in a galvanic cell. If you don't show a concentration, the assumption is that the concentration is standard or 1 mole per liter. Okay. You can show the states as well, so we can show that this is a solid, okay, but it's not required. Okay, in question 2, it says to write the anode and cathode half reactions for the galvanic cell. And we'll also write the overall cell reaction for this. So the nice thing about the way that these are written, like I said before, is that we can see right away what the reactions are. So we know that the reaction on the left is the anode reaction, so we're going to have a loss of electrons, in this case 3 electrons. And then on the right we see the cathode reaction, which is reduction or gain of 2 electrons to form lead. So these are the two half reactions. If we want to show the overall reaction, we need to make sure that the electrons are balanced. So in this case, we'd need to multiply the aluminum reaction by 2 and the lead reaction by 3. And so the overall reaction would be 2Al plus 3Pb2 plus goes to 2Al3 plus 3Pb. Okay, so this is the overall reaction. When you're showing the half reactions, it's appropriate to either show the full reaction balanced with the correct number of electrons, or this would be appropriate as well, just showing the aluminum going to aluminum 3 plus 3 electrons.